and let's take a look at what we're interested in today. All right, can someone before we start just give me verbal confirmation that you can see the slides and they're being shared to you properly?
Looks good.
Awesome, thanks. All right, so today we're going to talk about optimization and modeling. So previously we talked about optimization and we talked about the processes that we go through to find global maxes and global mins. Now we're going to talk about sort of just applying this to many different situations and what that looks like. So my first recommendation, as sort of dumb as it might be, is really just to read this chapter. We will, of course, do examples right now, and I'll walk you through the processes, but the main thing with this section is practice. And there are a lot of good examples in this section for practice. So my recommendation would be read the problem statement of the example, start to solve it on your own without looking at the solution, and then you will get stuck. And when you get stuck, go and look at the solution, and it will be extremely helpful in that regard. Because then you'll realize, oh, I'm getting stuck on this part, and I just need to realize that blah, 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 you know? So I think that will be very helpful. Okay. So what do I mean by this? Well, this section is pretty much only examples because it's just applying what we've already learned to more like word-like problems. So we're going to start out with the following example, and I'll read it to you first, and then I'll sort of just draw a picture. So a rectangle has one side on the x-axis and two sides on the curve, and then it gives an equation. And now we want to find the vertices of the rectangle with the maximum area. So the first thing that I always like to do is, if it's possible to draw a picture, I want to draw a picture. So I know that this curve sort of looks like this. Not like that, but like that. So it has a horizontal asymptote at the x-axis. And I know that I'm trying to fit a rectangle under it. So I'm going to draw a rectangle under it. And it also told me that one of the sides of the rectangle is on the x-axis like that. A little crooked rectangle, but hopefully you guys get the idea that I'm just fitting this rectangle under this curve. And the question is asking me, find the vertices of the rectangle with the maximum area. Maximum area. So I have some parameter. This is how most of these questions are going to go. I have some parameter, area, that I want to either find its global max or its global min, right? So for example, if I'm trying to minimize cost, maybe. But in this case, the parameter I'm looking at is area. Okay, so let's see how we set this up. So I'll go back to the picture I drew in just one second. So the next line says, we know area is width times height, right? That's familiar. And we know that we're bounded by this graph. So let's take a look. We just said that area, the parameter we're looking for, this is width times height. And down here, we have our width and we have our height. So now I need to be able to write width and height in terms of other things that I know. So this picture, it's not clear from the way I drew it, but this picture is symmetric about the y-axis, okay? And if you're not convinced of that, you can plot this guy on Desmos, or you can graph it on your calculator yourself, or you can just look at the equation and notice that, well, if I plug in a negative number to x, it's x squared, and x, so it's not going to care about whether or not I'm plugging in a negative or a positive, right? Because the term is always squared. So this length here is x, and this length here is x for some x, right? So the width I might write as 2x. Okay. On the other hand, if this length here is x, I'll use a different color maybe. If this length here is x, okay, then this height here is f of x, right, which is 1 over 1 plus x squared. So in other words, I can write width times height as 2x times 1 over 1 plus x squared. I'm going to pause. Is everybody with me so far? Anybody confused by the setup so far? I'll check the chat. Alex is with me. Okay. Hopefully more than just Alex is with me, but we'll keep moving on for now. But please do interrupt me if you're confused by anything that's going on. Okay, so let's move on. So we have this formula for area, right? We just said area is width times height, and well, width times height we can write in terms of x. This is the crux of most of these problems, okay? I want to be able to take the parameter I'm looking for, area, and I want to write it in terms of one variable. This is calculus of a single variable, so that's as bad as it's going to get. So I had it in terms of two things, width and height, okay? But I can write those two things in terms of one thing only, x, and that's much better. So now I have an equation for area, 2x over 1 plus x squared, and I want to maximize that. Okay. So this is just what I was saying. If I have a vertex at x, then I have a vertex at 1 over 1 plus x squared, excuse me, and similarly over here. Those are just my vertices. So that's what I was doing. I was writing out our formula for area in terms of x's. Now we're looking for a global maximum. Okay. So when we're looking for a global maximum, now we've reduced it to what we talked about last time. Okay, we did all this setup, all this analysis of the situation. Now all we have to do is just say, oh, let's use our tools that we know about optimization. So our tools about optimization tell us we have to take a derivative, right? We have to find the critical points first. So find, excuse me, find the critical points. In order to do that, we have to take the derivative, which is why we're using the quotient rule. So now we have to use the quotient rule on a of x. So let's take a look at what that looks like, and I'll walk you through it. So a prime of x, we're going to treat this as the numerator, and this is the denominator. So a prime of x is low, d high, well, the derivative of 2x is 2, right? Minus high, d low, derivative of 1 plus x squared is 2x, okay, over low squared. So now I just have 1 plus x squared on the bottom. Okay. And then we're going to do some simplification in the next step. So I multiply this thing out. I get 2 plus 2x squared minus 4x squared over same numerator. Okay. And then I'm just going to factor again. So, did I do something wrong? Hang on. No, I just subtracted. Sorry about that. So these terms subtract because they're both x squared. So I have 2 minus 2x squared, and then that just becomes this in the numerator. And there shouldn't be a parentheses here, and the denominator is just the same. Okay. Any questions about this part? Taking the derivative, any of that? I'm going to keep going then. Check the chat real quick just to be sure, but no questions in the chat. All right, so we have our derivative, and again, an extra parenthesis, sorry about that. And we can check when it's 0, right? Because we're looking for critical points. So we're looking for when this thing is undefined or when it's 0. Well, when it's 0, we can just look at the numerator, right? So when this thing is 0, that's at x equals plus minus 1. Okay. But we just said, as per previous observation, we just said when we're looking at, a vertex, like plugging in 1 and minus 1 gives us the same outcome in the original function a. Same outcome in a. Okay. And so our answer we're just going to consider the positive one. Okay. So in this case, you might get confused because looking at like negative would be like, oh, it's negative distance, but it doesn't really matter. So we're just going to throw away that answer because they're equivalent, and we're just looking for one global max. So let's just look at one. And the other thing I want to mention, is that we're looking for. I'll go back to the diagram so we can visualize it together. We're looking for any set of vertices which is going to give us a maximum area. So we're not bounded in some closed interval like we had last time, like 0 to pi over 2. We're not doing that here. Here we just have the big open interval minus infinity to infinity. So in particular, we're worried about the situation where maybe I have like a very long and skinny rectangle with vertices like that in the orange that I just drew. Okay. So we're worried that maybe the end behavior, we can get a huge rectangle by just making him very long and skinny, right? So we have to look at the limiting behavior because for 4.2 we said open intervals, we have to look at the limiting behavior. So let's do that. We have to look at the end behavior of our original function as x goes to plus infinity and minus infinity. Okay, because those are the endpoints of the open interval. Okay, but as we so I'll write this out a little more. It's not done in great detail in the slide, so I'll write this out a little more. So we're looking at this limit, right? That's what we just said. 2x, 1 plus x squared. Okay, but this is a rational function. Okay, and we said that for rational functions, if the degree of the denominator is strictly larger, right? If the degree of the denominator is strictly larger, then as we go to infinity or minus infinity, either one, we get 0. So neither of these things are going to be a maximum, right? Because I can put a rectangle of positive area under there. So this guy would be like approaching a global min. But we're looking for a global max. So that's good. That means our long, skinny rectangle worry is not going to happen, basically. Okay. So that means that the point that we cared about, 1, is really the only one we're now worried about. We just want to make sure that it is a global max. So we plug it into the original function. So if we plug it into the original function, we use the fancy plug-in notation. We have 2x over 1 plus x squared. We're evaluating it at x equals 1. Do some basic math, and we get 2 over 2, just plugging in. And then that's 1, which is, of course, larger than 0. That's good. That's what we wanted to see. Because the end behavior gave us 0. So if we're getting a true global max, then we should get some positive thing. So our global max, the area of our rectangle there is 1. Okay. But we're not quite done. I'm going to take a break. We're not quite done. We found the area at a global max, but what was the question asking for? It was asking for the vertices of the rectangle. So we know that the global max occurs at x equals 1. So one of the vertices is 1, right? Because x equals 1, comma, and then the equation we know is 1 over 1 plus 1 squared, which is just 1 half. Okay, so that's one vertex, but this is mirrored around the y-axis. So that means we have the other vertex minus 1, which again is why we didn't care if we picked 1 or minus 1, because it's all the same. Sorry, that should be a minus 1. So we have another vertex there. And then we said that the other, when we drew our picture, the last side of this rectangle lied on the x-axis, which means that the last two vertices we're looking for are 1, 0, and minus 1, 0. All right, take a long, long pause, and I'm going to check the chat for questions. If you don't have a question, would you mind saying that you're all good and you're happy with this? Something like that in the chat. But if you do have a question, take your time, formulate it. Okay, we have a couple people who are good. Feeling, are you raising your hand? Or I can't tell if that's like a happy emoji or if that's like raising your hand emphatically. Happy. Okay, good. Awesome. All right, everyone's good. Fantastic. So that is the crux of this section. I want to go back through real quick before I get to sort of the last part I want to talk about. The crux of this section is take a scenario, right? We had a scenario, and write it in an interpretable way. So we have all this nonsense. We drew a picture to make more sense of it, and then we wrote the thing we're trying to maximize, A, in terms of things we could understand, and then we did it one more time. We wrote it not just in things we could understand, but in terms of one variable and one variable only. Okay, and that way, because it was in terms of only one variable, we could differentiate and look for critical points and carry out our whole process as in 4.2. Right, so 4.3 is really just how do I stare at a problem and make it into mathematics. Okay, so the slides were sort of short for this, so I'm going to take a look at the worksheet real quick, and I'm going to do the first one on the worksheet with you as well as another example. And then we will close out the recording and just call it for questions, and we can talk about whatever else we need to. Okay, so I'll read the question with you, and then again we'll walk through the process. So the City Council is planning to construct a new sports ground in the shape of a rectangle. So again, draw a picture. Shape of a rectangle with semicircular ends. So something like this. Okay. A running track, 400 meters long, is to go around the perimeter. Okay, so 400. What choice of dimensions will make the rectangular area in the center as large as possible? Okay, so now I'll look to the chat for an answer. What are we trying to maximize here? What are we trying to find the global max of? I'll keep showing it for just a moment longer. What are we trying to find the global max of in this question? Okay. The rectangle, you're very close. You're on the right track. Yeah, the field. Exactly. So you're on the right track with the rectangle, but we want to know, oh, actually that's my bad. I misread the question, Zoe. I'm sorry. What choice of dimensions will make the rectangular area as large as possible? Yeah, Zoe, you're absolutely right. Sorry about that. Yeah, I thought I misread it. So we need two equations. We have a constraint, and we have like a parameter we're trying to maximize. So I'm going to just call that what we want. Okay, what we want is the area in the middle, which I'm going to call A. Zoe's absolutely right. It's just the area in the middle, not the entire area in the track. And I'm going to label the sides. Okay, I'm going to label width and height. And just like last time, area is width times height. Okay. Our constraint is we have to have that the perimeter of this whole thing is 400. So let's count up and use geometry to figure that out. So the perimeter, this thing is W, this thing is W. Oh, sorry, a bit. It's a bit fat for the marker. W, W. This is not on the perimeter, so we're not going to worry about H. So we have two W's. And then over here, this length, that's half a circle, right? So the circumference of a circle is 2 pi r. So half a circle is pi r and pi r. And then the question is, what is r, right? Well, r is this, okay? But we just called that quantity h. Everyone see that that's an h? Called that quantity h. So r is really just half h. So it's pi h over 2. And similarly, pi h over 2. Okay? So the constraint is that when I add all these things up, when I have 2w plus pi h, I have to use 400. And now what confuses some people is, well, I don't have any x's in this question, so how do I get w and h in terms of x's? Well, last time our constraint was the curve, and that's where we got the x's from. This time our constraint is just this weird equation, 2w plus pi h is 400. So we're in our constraint, what we will always do, how we will always solve these problems, is we will solve for one of the variables in our constraint, whichever one we think is easier. Okay. So I'm going to pick w, because I think that's easier to solve for. So 2w is 400 minus pi h. So w is 400 minus pi h over 2. Okay. So why did I do that? Because now I have a way to relate the two parameters w and h. And because I've done that, I can now write a in terms of just one variable, w. So I get a is w times, oh, I'm sorry, a is, w times h, which is, we said w was 400 minus pi h over 2 times h. Okay. I'm going to pause, and if there are any questions, please say something or put something in the chat. I also have a question I want to ask. But if you're okay, just give me like a thumbs up or an all good. So far, all good. Everybody's all good. Awesome. Okay, so my question to you then is, what is my next step? So I just set all this up. Okay. I now have an equation for a in terms of one variable. That variable is h. What is my next step here? And if you're not 100% sure, go ahead and take a guess, and we'll go from there. I'll just leave that out there so you can take a look at the work as you're thinking and maybe typing. What is my next step? Find the limiting behavior. Find the limiting behavior. So I'll get into why you don't have to do that here. So find the derivative is right. Find the derivative. So we want to just find the derivative, but what might confuse people is that there are no x's or anything here, right? But it's okay because a here is a function of h. So I'm just going to differentiate a with respect to h. So dA dh is the following. And before I differentiate, I'm actually going to multiply out to make my life slightly easier. So I get 200h minus pi h squared over 2. So my derivative is 200 minus pi h. Okay. So now I'm going to set this equal to 0, right? So my derivative, this is a really nice function here. It's defined everywhere. So there's no, there's no undefined points in my derivative, so I only have to care about when it's equal to 0. So I set this equal to 0, and now I'm solving for h. So I get 200 equals pi h, which means, of course, that 200 over pi is h. In other words, this guy is a critical point for A. Okay. But now we get to Aaron's question. And Aaron's question is, do we have to look at the limiting behavior? So now here we have to sort of interpret what is our region that we're looking at that is reasonable for this thing. Okay. So if we have to use, if we have to have some kind of area, then it's reasonable that we should be looking at the interval where we have 0 height, right? That's sort of like the dumb scenario. It's like you built a straight line instead of a field. Versus the max amount of height that you can have, which is, I guess, let's see, if you built max amount of height you can have, you certainly can't have more than the perimeter. So like the maximum bound would be 400. But we'll see why that's sort of unnecessary. But the reason I do that is because I want a closed interval so that I don't have to care about limiting behavior. Right? So I can't possibly use more than the whole perimeter in just my height. And I can't possibly use nothing in my height. So that we know that our answer for our global max is definitely contained in this closed interval. That's good because our formula for finding these things is much, much better on closed intervals. We don't have to do any limiting arguments. So now we only have 3 points to look at. This point for h, this point for 0, and this point 400, right? All of these potential values for h. But these guys, we just described what 0 and 400 were. These guys here. 0 and 400 gave us degenerate cases with no area. So those are going to be bad. So it should be this guy, 200 over h. So I have to plug that back in to our original formula, A equals WH, and see what I get. And as long as it's better than 0, we know we have a global max. So I'm going to erase this a little bit right here. So we're plugging back in. But again, we said W depends on H. So I'm going to use this formula for A instead. And actually, probably this is even easier. So I have 200 times H, so I get 200 squared over pi minus pi times 200 over pi squared over 2. And then if we've done this right, which hopefully we have, we get 200 squared minus pi is 200 squared, and then I have a pi squared on the bottom here and a pi over here, so those one of those is going to cancel with one of those. So I have 200 squared over 2 pi, which is 200 squared over 2 pi, which is a positive number. So I did get a global maximum, and all is well. All right, so that is how we would solve that problem. Again, I'm going to pause for questions, any kind of final questions that we might have. I'll show you just the screen again, just in case you need to look at that work one more time. But if you're all good, remember to type something in the chat to just say you're all good. And if you want me to back up and go over something again, please just say that. I'm more than happy to do it. Okay, 3 people are all good. Others are still thinking, digesting. I have Daeshun, Aaron, and Zoe. Yuling, Alex, Evan. Are you guys happy with this? Evan's good with it. What's the answer? I think the answer is, so what choice of dimensions? So we just gave one choice. We just gave h. Okay, so the full answer, Alex, would be that h and the w that you would get from plugging in h back to this formulation for w right here. Okay. I'm going to stop the recording there.